that video, and that is why I have shared that video on the YouTube. From now onwards, you are going to get the video on the same Meet, because from now onwards, I am not going to upload on the YouTube. So now you can see my screen, and whatever I am doing, just try to practice by yourself. And if you are facing any issue, means you can type either in the comment box, or you can just go to the Gmeet link, and you can ask any of the questions from our mentors. Okay. So OF6 I have typed, it means that I have created the OpenFOAM 6 environment. Okay, that we have already seen in the study class. Now, if I want to go to the our run folder, so we can go cd means we want to change the directory, and we can directly go to the our run folder. Okay, here I have created one folder for day 2. So week 1 0 day 2 I have created one folder. So we can go to that folder. You can, if you want to create this folder, you can just use the command mkdir. So make a directory. That command you can use, and you can type this name, that is week 01 and day 02, and you can create this folder if you want. Okay. Now if I type here, there are already some of the cases that I am going to cover today. But let's copy one test case from the OpenFOAM tutorial folder. So I will go to the OpenFOAM tutorial folder, and I will go to the incompressible, and I will go to the icofoam. Okay. First let me list out that what are the test cases are available here. So if you are using ls command, it is going to list all the directory present at this given location. So if I list here, you can see here that these two different folders is available, that is the cavity and the elbow. And even if I go to the cavity folder, then there are different cases are available, that is a cavity clipped, and cavity graved. Okay. So we can copy this cavity folder, and cp-r, and since we want to copy that folder to the current location, that is why we need to put that dot. Okay. So the complete instruction of this command is that we want to copy a directory at a present location, that is why I am putting this dot here. Okay. So now you can see that there is a cavity folder. So we copied a test case from the tutorials folder, and I have copied here. Okay. As I instructed yesterday class that we should not change anything in the by default OpenFOAM installation folder. Even if you want to run a test case, either you want to run a compile a solver, or you want to modify a solver, you should not touch anything of the OpenFOAM by default installation folder. Okay, so that is why we should always work in our run folder. So if I go to the cavity folder, here these are the folders, that is the 0, constant, and system folder. So as I said yesterday that this 0 is for the boundary conditions, initial boundary conditions, initial field values. Constant is for the mesh, and different thermophysical properties are the different properties, give turbulence properties kind of things are given in the constant folder. And system is for the every scheme, every solution, and the meshing information is given here. Okay. So now let's go to the these three folders one by one, and let's see that what is the FB scheme, what is the FB solution, and what is the control dict. Different parameters are given here. Constant have different parameters, and 0 folder has given different parameters. Okay. So let's see these three folders in the depth. So if I open my this slides, so if speaking of the 0 folder, so if you open the 0 folder, so you can see here that different field variables are given here, that is u and p. And if I open this u in a text editor. So you can either use the Vim or you can use other text editor. Okay, so if you want to use your own text editor like Genie kind of a text editor or some notepad kind of text editor, then you can directly go to the folder and you can directly open this in the text editor. So either way you can open this text file. Either you can use your terminal or you can use any of the text editor to read this different field. Okay, so if you see this folder, this U field, so here it is given that U is a volume vector kind of a field. Okay, since U is a vector field, and then since U is defined in a volume of the every message. Okay, so that is why it is called as the volume vector field. Okay, we are going to understand this volume vector field, volume scalar field in the more details while we are going to do this, while we are going to create our own solver from the zero level. Okay, so this is the first information given for the that field that has been created in the zero folder. Okay, so it is saying that the object U has been created, and it is saying that this is the value vector field. After that, if you go, then you will find that what is the dimension of this U, that field that you are means defining in the zero folder. And the syntax of this dimension is like this. Okay, so this is kind of a enumeration you are creating. Okay, and first is the mass, second one is the length, third one is the time, fourth one is the temperature. After that there is the moles and current and luminosity intensity. Okay, so for example, if you want to define some quantity, for example, if you want to define some variable who has only information of the mass, in that scenario we are going to specify that mass has one, other quantity has zero values. Okay, similarly, if you want to define some variable or some field who has only length dimension, the rest is the zero, then we are going to give such kind of the definition here. Okay, so since we are defining here velocity is length per second, that is the meter per second, then this is why you can see here that this is mass is zero, length has one dimension, per second that means -1, and other dimensions are zero. Okay, when we are going to understand a dimension type, then I am going to explain about how this enumeration has been defined in the OpenFOAM. Okay, for now you should just know that this is the format of defining a dimension in the OpenFOAM. Okay, so you can see here that you can also work for the chemical reactions, you can work for the current means electrical problem, you can also work from the optical kind of problems. So that is why this OpenFOAM can solve the different kind of the physical phenomena, and these are the seven different dimension you can see here. So you can define any kind of the variables that is needed for your problem. Okay, now once dimension is defined, after that there is internal fields. Okay, so for example, for velocity, it is saying that in every internal cells define the velocity as the 0, 0, 0. Okay, because it is the vector field, so that is why it has the three different values in the three different directions. Okay, if you open for the pressure field, since pressure is the scalar quantity, so you are going to define pressure as a scalar field, and that is why you can see here that this value is only one value, and it is going to define in the every cell center of the given mesh. Okay, so this is where you are defining the internal value at the initial state, initial boundary condition. Now this is the boundary field. Okay, now why this internal field is important, this value is why important, that depends upon the your problem. Okay, for example, if you are solving the incompressible steady state problem for a single phase simulation, then initial condition is important because initial guess can speed up your convergence. If you are if you have done means simple form kind of a in-house coding, or if you built any in-house coding at your CFD basics levels, then you should know that this initial guess in incompressible steady state is important because initial guess can speed up your convergence problem. Okay. Now, in case of the compressible flow, this is important because in compressible flow, we solve the equation of state to find out the pressure field or the different means other different fields. It is important because many properties or many fields are depends upon the equation of state. So in compressible flow, this internal field is important because we solve the equation of the state. Okay, in multi-phase problems, initial values are important because here we are going to solve the different phases, and this interface capturing is very important between the different fluid or solid phases. So in that way, in multi-phase problem, this initial values is very important. Okay, but since here we are only using the icoform, so we can start with the zero values. Okay, but when you are going to the multi-phase problem or the compressible problem, this initial guess values are very important because of this two reason. Okay, now in case of the different internal means like multi-phase flow, sometimes this different values that is specified in the zero folder of the test case can be modified using the some other post pre-processing utilities. Okay, for example, one utilities I have given, that is the set field dicts. Okay, so this kind of the utilities can be used to modify this means this different fields mentioned in the zero folder. Okay, we are going to do one test case related to the interform, and then means we will see the example that how this set field is important. Okay, so this task we are going to do in this class, in this present means after doing this simulation for the this icoform. Okay, so I will request everyone to just follow the instructions. Okay, so we can create the mesh using the block mesh. Okay, now since we have taken the icoform, we can run icoform command. Okay, now here is one catch. If you want that whatever the things are printing on the screen, you can just print that means that different things that print, you can print those things in a text file by following this command. Okay, you can use this log and this hyphen command. So whatever after running this solver is going to print on screen, that is going to be saved in a text file that is named as the log. You can give any name, like you can give it as a log.icoform. So that is going to save everything screen output on this text file. Okay, and you can run that. Sorry. Now, if you want to read those text file, you can use this tail -f and this name of that text file. So you can see here that whatever this icoform solver has done on the screen, it has been printed in this log icoform, a text file. So if you want to go to the test case, you can see that there is one text file has been created, and if you want to open this in any text editor, you can open it, and you can see here that starting from the 0, it has been read the transport properties different field, and it has been saved. Every iteration has been saved as a text file in your test case. Okay, so sometimes if you are running a means large problem, then it is required to save every text, every iteration as a text file. Then this two command is very important. Okay, so like you can means your solver name is can be anything, and you can print this output in your any text file name. That could be any name. Yes, Raj, you have any question? Hello.
Hi, Pratyush. I just missed the command CP, copy, the copy command, right? From
Yes,
the,
if you want
okay.
to copy,
Yes, yes.
so this command cp minus r,
See,
and the case that you want to copy it, and this dot is for that you want to copy in the present location.
okay. Can you please come again? CP minus R,
Cp minus r is stand for
dollar.
that you want to copy a directory.
Yes.
Okay, and this is the location of that cavity folder from where you want to copy.
Okay.
Okay,
Previously, the last tutorial you used a dollar form dot tutor minus tutorial, and
yes,
then
yes,
you
yes,
press.
see this, see, if you are doing cp minus r,
Yes.
and this dollar is for the form tutorial.
Okay.
Okay, and as soon as you are going to enter the incompressible, it will show the location here. So this is one kind of a variable that has been stored as the dollar form tutorial.
Mm-hmm.
Okay, so as long as you are entering the form tutorial, it is going to directly enter to the this location.
Yes.
After that, we are going to the incompressible icoform cavity, and this dot is used for the that you want to copy in the present location.
Okay. I form cavity dot.
Dot
That's
is
enough.
further that you want to copy in at the present location.
Yeah. Present location.
Okay.
Yes.
Yes.
Thank you. Thank you.
Yeah. So you run the block mesh, and after block mesh, you are going to run the icoform. This is the solver name. And since you want to that whatever printing on the screen should be saved as a text file, that is why you are using this sign, and this is the name of the text that you can give any name, and this is dollar. And if you, sorry, we need to go to the cavity case. Okay, so this is dollar, and now if you want to read that log file or text file, you should use the tail minus f and the name of that text file. Okay, so this solver has been done. Now let's explore everything of the this cavity test case. Before going into the solution, let's understand the every folder of this system and the constant. And then we will go to the interform, and we will solve this task after understanding the different FA schemes and solver control. Okay. Now, if you go to the after zero folder, the next important one is the this system folder. Zero is for the initial boundary condition as well as the initial guess value into the internal fields. Okay. After there is a system folder, and system folder has a three important folder, that is the control dict, FB scheme. Yes, 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 Raghu. Uniform zero means every internal field has specified a zero value. That is the meaning of the internal field. Okay. Now, see, there are three things. While you are going to solve a problem, any physical problem in OpenFOAM or in CFD, there is three things. One is the solver, second one is the schemes, and third one is the solver control. Okay, solver that you are specifying in your that you are developing a solver, that is just saying that what kind of the algorithm that you are going to use, what kind of the means coupling between the pressure and velocity you are going to use, that everything governing equations are going to specified in the solver. After that you create the mesh and you are going to now after creating a mesh and after creating a solver, you are going to specify the schemes that the different terms of the given governing equation should be solved in a using this different schemes. That schemes is defined in the this FP schemes. What I mean to say that if you go to the tutorial folder, solver folder, and if you go to the application and if you go to the solver, there is an incompressible, and that ICO solver we are using here. Okay. Now if I open this .c file, so this is the equation that we are solving. Okay. This complete, this is the Navier-Stokes equation, and of course there is a pressure velocity coupling. But in a way we are solving a temporal term, one divergence term, one Laplacian term, and here is the gradient term. Okay. And of course if you are going to write another equations, then there will be also Laplacian term, divergence term. So this different terms you have specified the equation here, but how this different terms is going to be discretized between the internal field, internal cells or the boundary patches, that is going to be specified in the schemes, FB schemes. Okay, so how this temporal term can be going to be discretized, how this divergence terms is going to be discretized, and this Laplacian term is going to be discretized. That is information you are going to give him in the schemes. Okay, so in a way we can say that differential, we are converting this differential equation into the algebraic equation uh, with the properties average in the finite values. So since we are creating a, while we are creating a meshing in OpenFOAM or CFD, we use the finite value method. Okay, now to discretize a different terms in OpenFOAM, there are two terms is important, that is implicit and the explicit, and that is where this FVM and FVC terms is comes into the picture. This FVM is called the implicit treatment, FVC is called the explicit treatment. Okay, so what does it mean by the implicit treatment, and what does it mean? It means by the explicit treatment. So remember that whenever you are going to do operations on the matrix, okay, then it is known as the FVM operation or implicit terms. But when a terms is added as a source term in a given matrix equation, then it is known as the explicit terms. Okay, so for example, if we write AX is equal to B, so in that scenario, A is a complete matrix that you want to solve. Here in A, there is a number of the unknown variables, but this B is act as a source term. These are the just a numerical value that is going to help to solve this A using the iterative method. Okay, so if you see this governing equations, so this three values, that is the temporal term, divergence, and Laplacian term, has been done a implicit treatment, and this after implicit treatment, it is going to create one matrix, and that matrix is kind of the FB vector matrix, and the name of the matrix is the UV equation. Okay, so this is the going to create a matrix because we are doing the implicit treatment. And after when you go to the solve the equations, then we are adding this gradient P as a source term to find out the unknown values from the this created matrix, that is the U equations. So that is why we are solving, taking this FVC grad P as a source term in this means algebraic equation that we are defining, that we are finding here. So that is the difference between the FVM method and FVC method. And this FBC and FBM already defined in the solver. So it is not going to be defined in the FB scheme folder. It has been already given in these solvers that we are creating while compiling our own solver. So I hope this FBC and FBM concept is clear to you, because it is very confusing and many people don't know about this difference between the FBC and FBM. Now, if you go to see the discretization schemes, there are different terms. Generally, these are the important terms in a given FB schemes folder. Okay, so if I open the cavity case that we have copied from the OpenFOAM folder. So if I open this FB schemes folder, so you can see here that these are the important terms that is generally, whenever you solve any equations, these are the terms that you come across. That is the DDT schemes, grad schemes, divergence schemes, Laplacian schemes, and interpolation schemes, and SN grad schemes. Okay. And the definition of this different schemes is defined in OpenFOAM in such that it follows the runtime selections. What is the runtime selection? The advantage of runtime selection in OpenFOAM that while you are running the simulation, you can also do the modification of any of these variables. Okay, so while you are running the simulation, and you can change this variable. Like this is the Gauss linear. This is the Gauss linear orthogonal, linear given, this orthogonal given, or Euler given. This kind of information you can change while running the simulation. You can change this Euler into the backward kind of the approach applied for the temporal term. So this information you can change during the runtime selection. So many things in OpenFOAM followed this runtime selection approach, and that is another advantage of using the OpenFOAM. So this is, if you go to the different schemes for the FP schemes folder. So if you talk about the DDT schemes, it generally it solves the temporal discretization, and there are many method is available in OpenFOAM, like Euler scheme, Craig-Nicolson method, Eulerian method, backward method, bounded, local error, and steady state. So steady state used for the steady state solver. Generally for transient, this co-Euler method and backward method is used. This Craig-Nicolson method also used. It has generally two values are given if for the Craig-Nicolson. So I am going to provide you a master FB schemes text file where you can learn about this different terms using that master schemes. So I am going to give you this master for the FB scheme, FB solution, and control dict. And you are if you are going to follow these different schemes, then you are going to understand that how these different approaches for discretizing the different terms are being evaluated in the OpenFOAM. This grad scheme is used for the gradient evaluation. Okay. This divergence scheme is used to discretize the convective terms, and generally in OpenFOAM, always this method is applied that divergence is always used as the FPM and implicit method. Similarly, if you are going to see this gradient schemes, it is generally used as the source term in the given governing equations. So generally, it is used as the FBC scheme. Okay, the Laplacian scheme is going to solve the Laplacian terms. This interpolation scheme is important because interpolation scheme is generally means going to find out the, since we always OpenFOAM always define the values in the centered value. Given cell, the centered value is defined. So if you want to interpolate from center value to the face center, this interpolation schemes is important. And using this interpolation scheme, it is going to find out the value at a given face. And from this face, that face you are going to means use for means calculate the different means once you defined at the face value, face center, then you can use to calculate the Laplacian values. Also you can use for the gradient scheme, and even if you want to use the different boundary condition, so this interpolation, once it interpolate up to the phase center, then you are going to use the boundary condition or the different Laplacian and divergence schemes. Okay, so this is just a brief about that how this CFD schemes works in the OpenFOAM. And in CFD class, some of the this important highlighted means like DDT schemes or gradient schemes. Like this Gauss is important for the gradient schemes. Similarly, maybe one or two schemes we are going to take for the divergence and Laplacian schemes, and that we are going to cover in the while we are going to cover the CFD classes, where we are going to just discuss about the CFD theory. Then we are going to cover the some of the important schemes that I have discussed here. But I am going to provide you this master file, and that you can use to understand the different options available for this. Like for DDT schemes, you can see here that these are the different schemes, and this is the first order. This is going to provide the bounded and implicit method is being used. So for example, if you are using Craig-Nicholson, this phi value you can take either 1 or 0. Okay, or you can take the value phi equal to 0.5. So if you are going to take 1, it corresponds to the pure Craig-Nicholson method. 0 means here it is going to use the pure Euler method. And if you are taking the 0 point, it is going to consider the both values. Okay. So these are the different options that you can use. So if you want to know that what should be options available for the given schemes, you can use a banana system. So what I mean to say that, suppose you want to know that what are the different options available for the transient term. Okay, so you can just type here test or any random name. Okay, and if you are going to run the solver, suppose I want to run the solver icoform, so you can see that it is going to give you different options for this transient this temporal term. So if you want to know what are the different schemes available for DDT schemes, you can just type the test, and it is going to suggest you this much options. Okay, so this is the way you can know what are the different options available here. Suppose if I want to know that what are the different options available for the grad schemes, then I can type here test, and if I'm going to run the icoform. Sorry. So here you can type here test, and if I going to run the icoform, so you can see here that different options it is showing here. Okay. So this way you can know what are the different options is available for uh, this grad schemes or the divergence scheme or the Laplacian schemes. And if you want to know something about then you can follow this master that I am going to attach in the your files of the Google Meet, MS Team. Okay, just please go through it, and we are going to discuss the mathematics behind the some of the important schemes in our CFD tutorials. Basic CFD, when we are going to discuss, we will going to know some of the important things like this Gauss linear is. So this u.swp, this folders generally created while we are using the sorry, while we use the in WSL thing. So this folders is not present in means like when you use the Ubuntu kind of things, it is not going to present here. So this is the, maybe you can say that this is the means not nothing related to the OpenFOAM. This folders that you are asking about, that what is the u.sw, this is nothing related to the OpenFOAM or CFD things. It creates while we are using WSL. Okay, while this kind of folder you will also observe while you are going to use the multi-region solver or multi-region test case. Okay, so just you don't know need to know about that at this level. Okay, so once you do the discretization, so we already know that what are the governing. Yes, hello. Okay, okay. Yes, yes. Abhishek, send me request. I will. Yes, Abhishek. Send me request. I will let you enter. Abhishek. Yes. I cannot see. No, I did not get a request to join. I'm not. Yeah, you might be facing the internet issue. Okay, okay, sure. Sorry, someone asking me to. So after every scheme, so we have discretized the means different terms of a given governing equation in the solver. We have a equations like ax is equal to b. We have a one matrix formed, and there is a one source term, and there is a x which has the different terms are the unknown variables. So this kind of equation we have formed here. Now we want to solve the given matrix, and that is where this FB solution comes into the pictures. It is going to tell you that what are the different, different solver treatment that you are going to apply to solve. Abhishek, can you mute your mic? Abhishek, can you mute your mic, please? Okay, so in session, we give the information that what are the different methods or technique or the tolerance or the relative tolerance that provide you that it is going to solve the given matrix that we formed after discretizing the governing equations. Okay, so in every solution, if you refer to the every solution, there are two main subdictionaries. Okay, so in OpenFOAM, we called this each file as a dictionary. So like blockmesh dict is also a dictionary, control dict also a dictionary, every scheme is also dictionary, this every solution is also dictionary. So if you open this every solution folder or a text file, so there are two important sub dictionary are important. That is the solver dictionary and this is the piso dictionary. Okay, so this is one sub dictionary you can say, and this is the another sub dictionary. Okay, and in every solution there are means in OpenFOAM there are two kind of the solvers are available. Okay, one is the solver that you are creating while compiling the solver, so that is known as the solver applications, and this is known as the linear solvers. Okay, so generally when we say solver, then we mean to say that solver application, but this is also this every solution also gives the information of the solvers. This is known as the linear solver. Okay, means that after creating the matrix, what are the different solution method that you are providing to solve the p values, and for solving the matrix related to you, what are the different solver information that you are giving, that information is provided in the every solution. Okay, now here if we speaking about the p, the solver, we are using the pcg, and for this preconditioner we are using the dic information. Okay, these things we will discuss while we means discuss these things in the in more depth, then we will know about the this pcg and dic. This tolerance you are providing, and this is the related tolerance. The difference between the tolerance, that this is important while you are solving the steady state solution. So either this should be fulfilled or this related tolerance should be fulfilled. So related tolerance means the difference between the means consecutive two iterations. Okay, so if the difference is less than 0.05, then it is going to show you the converse solution. Either it is going to see further whether this tolerance criteria is fulfilled, or it is going to see that whether this relative tolerance criteria is fulfilled. So if either of these two is fulfilled, then it is going to show you a converse solution. Okay, this p final is important when we are going to use the relaxation factor. Okay, similarly this for the you are going to get the tolerance that is 1 e to the power minus 5, and this here we are not providing any relative tolerance. So in such scenario, it is going to just look for the whether this tolerance criteria that is 1 e to the power minus 5 is fulfilled or not, and when it is fulfilled, then it's going to show you the steady state solution. This is best for the solver that you are using. Like if you are using the pimple foam, then different variables related to the pimple foam you are going to provide. If you are using the simple foam, then different variable related to the simple foam that you are going to provide. Similarly, for the means piso foam or any kind of algorithm that you are going to use, this information is going to provide for that that means the appropriate algorithm that you are using for the given server. Okay, so in piso foam, these two variables is important, that is the en characters and en orthogonal character. Okay, so these two things is important while using the piso foam. While you are going to use the pimple foam, there are more other two other terms is going to be added here. So when you understand the algorithm, then these two things will be clear to you, that what is this n characters and n non-orthogonal characters. Okay, so while whenever you're going to provide the every solution, so these two sub-dictionary is important for you. One is related to the linear solver and one is related to the solver applications. Okay, so I have also provided one master folder for the visualization. You should also go through that master. Okay, so I think this is up to this you are clear that what are the different folders available in different this cavity folder. Now this is important. Another important folder is the cavity control dict. So this is all about related to the time control. Okay, so here you are written that we are using the icofoam solver, and these things we are using that what is the start time. Okay, so if you want to know what are the different options here, you can use the test here, and if you run the icofoam, so you can see here that it is expecting three variables. Either you can specify the start time, or you can use the first time, or you can use the latest time. Okay, so this three value can be used if you want to use for the start from. Okay, maybe let me open the this master of the control dict. Okay, so you can see here that these three variables that you can use for the start from. So when you write the start time, it is going to start from the zero folder. Okay, but sometime it happens that you have run a simulation and you have some time folders, like here you can see that 0.1, 0.2, 0.3 and 0.4 and 0.5. Okay, now you want that you just want that you start simulation from the 0.3. Okay, suppose you want that you want to run the simulation from the time value 0.3. So in such scenario, you can specify here that start from the latest time. Okay, so when you are suppose you are solving some transient problem and you have a number of time step you already solved, and your system has shut down or some issue technical issue you have faced. So you don't need to solve from the again from the zero folder. So in such scenario, you can just specify that start from the latest time. So whatever the different time folder is available here. So in our scenario, like 0.1 to 0.5 time step is available here. So you just want to solve the your governing equation or solver from the latest time. So it is going to take your different values from the 0.5 and it is going to solve the solver or the governing equation from that time step only. So that is where you need to specify the latest time. Okay, this is the things that you want to stop. Okay, so for the stop at, there are different options that you want to stop at the end time. So here the end time is the 2000, so it is going to end at the 2000. Okay, if you are solving the transient problem, then it is going to end at a 2000. Otherwise, if you are solving the steady state, then it will end when it will reach the convergence criteria. Okay, now the stop can be also stop at the next write. Okay, suppose you started from the 0.4 and you are not writing at every time step. Okay, so here three things is there. This start time and end time, this information is related to the your simulation or your iteration value. This write control or write interval is information that at after what time, what interval you want to write a folder. Okay, so sometimes the time step you are taking, that is 0.01 or 0.02. So you don't want to write every time step folder, you want to just write a specific time folder. In such scenario, this write control and write interval is important. Okay, so here that is important, that when you want to stop, so as soon as you completed your next write folder, it is going to stop at that time step. Okay, suppose we are taking delta t is equal to 0.1, and after every 50 write interval, it is going to write a one folder. Okay, so once it completed the write interval and it is going to write a folder, as long as it is writing a folder, it is going to stop at that time step. Okay, this is going to stop at the no, this is no write now, so it is going to not write a folder, and as long as it completes that interval, that write control interval, it will stop at that time step, but it is not going to write any folder. Okay, this right now is that the current time step, the current time step it is going to solve, it is going to write a folder and it is going to stop at that time step. Okay, suppose I mean to say that suppose it start from the 0.3 time step and it is, you are writing that it will going to write a folder after the 50th iteration. But when you specify that right now is stop at the right now, it is going to write a folder at the just next iteration, and it is stop at that iteration only. It will write a folder and it will stop at the same time iteration. So these are the different important thing related to the stopping criteria. But mainly means every solver in OpenFOAM I see only the this end time. Okay, here this start time and latest time is important, but for as far as seen solvers, this end time is important here. This end time already explain you this delta t, that means it will start from the zero, and what should be the this delta t difference between the different iteration, that is specified here, delta t. And this is the for writing the different folder after different iterations. So this is time, either you can use the time step or you can use the adjustable runtime. Okay, and this runtime is also important, but this clock time and CPU time means I have not seen any test case in OpenFOAM, but this adjustable runtime is important, runtime is important, and type step is important. Okay, this adjustable runtime is important while you are going to use the multi-phase kind of solver. So in such scenario, this coherent number is very important. Okay, while you are going to solve the compressible flow or interflow or the multi-phase solver, in such scenario, you are going to use the adjustable runtime. Okay, so what it means that this, it is not going to solve for the delta t that you are specifying. It is going to look for the maximum coherent number, maximum alpha coherent number, and maximum delta t. So based on this information, it is going to calculate the delta t by itself, and it is going to solve using that delta t. Okay, so sometimes it will take 1 into 1 minus t, in next iteration it is going to take the some other delta t value. So this is variable things, this delta t is not fixed, but fixed is the maximum coherent number. So based on the coherent number, it is going to calculate the delta t. And if you want to that every after every adjustable runtime, it is going to create one folder. Then these things you are going to specify here. Okay. So if you want to use the adjustable time step, then it should be yes here. If you want to not use this, if you want to use just use this delta t, then you should write here no. Okay. So it will going to fix the delta t and it will solve based on this delta t, but it is going to give you some error by if you use the multi-page or compressible kind of the solver. That we are going to see when we means cover the multi-phase flow problem. Okay. This purge write is important because in where you would solve the steady state kind of solution, so generally the last folder or last two or three folders is important for you. Okay. So for example, I am solving the steady state, suppose I am solving the steady state problem. So only the steady state solution is important for me, not the every folder is important for me. So if I specify that purge write is equal to 1, so it is going to only create last folder. Okay. So what I mean to say that it will solve from the 0, it is going to create 0.1 folder. As soon as it is going to create 0.2 folder, it is going to delete the last one. Similarly, it is going to create 0.3, and as long as it will create 0.3, it is going to delete the last one. So only one folder is going to created while using this purge write. Okay, so let me show you example. So here it is 0 written. If I write here 1, so let me create all the time folders, and you can see here that there is no any currently there is no any time folder. Now if I run the icofoam and if I open, here, so you can see here that only one folder is written here. After running the solver, only one. Okay, so what happens? It only going to write one folder and it will delete the last one, and then again create one, then again it will delete the last one. If I write 2 or 3, it is going to only save the two folders, two last folder it is going to see. Similarly, if you can write the 5 or 10 based on your requirements, so it is going to only save the last 5 iteration, five last folders it is going to save. So this is important when you are going to solve the steady state problem, and if you have a messing which is taking around miss your lots of memory. Sometimes it happens that like when I solved the packed bed problem, it used to take the 2-3 GB for a simple one mess folder. So in such scenario, I need to use the this purge write so that it will only save the last iteration solution. Okay. Now this write format, either you can use the ASCII format or you can use the binary format. Okay. Again, if you have a large messing problem, then this binary should be preferred because it takes the less memory. Okay. This ASCII kind of the format takes the huge memory amount, and this binary kind of takes the information very less amount of the memory. Okay. So but it is important when you do the means complex problem, but for the cavity kind of simulation, it is not, this parameter is not important here. This is precision of the solvers, the different fields that you are solving. So this is the precision that you want to, after decimal it will take around the 6 decimal precision solution it is going to provide. If you write here 4 or 3, it is going to provide the solution up to the 3 decimal. Okay. Sometimes it is important that whether this folders that you are creating, that is 0.5 are different folders, you want that this folders it automatically compressed form, or I wrote automatically in the zip format. So in such scenario you can turn on this. Okay, so this is going to provide you zip kind of the compressible folder, compression folders, if you turn on this variable. Okay. Again, this runtime modifiable is important things. Okay. So it means that runtime modifiable means during the simulation, if you want to modify any of the parameters that is mentioned in the control text, and that it should solver should consider that modified variable, then you should means usually used here true. And if you want that this information during the simulation, if you don't want to consider, then it should written here the false. Okay, so this is another another application of that I have mentioned here, that OpenFOAM has advantage of this runtime selections. Okay, so for control dict, if you are using this true, then it is going to consider the runtime information, and if you are using the false, then it is not going to consider the runtime information. Sometimes if you are going to create your own boundary condition, or like if you want to use the swag for kind of the means application or solver use in your own solver, then this library can be attached here in the control dict folder. Okay, so like this groovy bc kind of boundary condition used from the swag for form. Okay, so we are going to install the swag for form also, and we are going to use one means a different like funky set field or a groovy boundary condition kind of the utility from the swag for form also. Okay, even if you are creating your own boundary condition or your own physical properties or the transport model, then this library should be linked here in the control dict information. Okay, and these are the different functionality. So when we are going to know about the function object, then we are going to see the some of the required information from here only. Okay, so maybe you can go through it. So like this probe function object that we use to get to pressure field and u field at it, this different probe locations. So this is the functionality of the function object in the OpenFOAM, that you can get the different fields at a given location. Okay, this y plus value you can calculate. Okay, so these are the different function object that we are going to see some of the important function object like y plus value and this probe location value. Okay, so this is the all about the control dict. So I hope every folder is clear. Here you can get the transport properties value like viscosity, or sometimes when you are going to solve the temperature equation, then thermal diffusivity information is also provided. Thermal diffusivity information is also provided in the. Yes, Akshay, what do you want to say? So some of the information is provided here related to different thermal physical properties. Okay, so this is all about the different folder structure of the given test case here. Okay, now this is the simple test case of the icon form. Let's see one test case related to the interform. Okay, so I have copied this dam break case. Maybe let me just remove this dam break. So we can copy one test case from the multi-phase solver, that is the interform. So let case from the laminar flow, and there will be dam break case. So I am copying this test case to our present location. Okay. So we have this dam break. So you can use this command, and you can copy this dam break into your present working directory. So if I go to the dim break case, you can see that again there is a 0, constant and system folder. So as someone said that we can run the all run command. So as long as this all run should be present here, you can only then run the all run command. If I open this all run in the editor, so you can see that it is running the only those options that we are running on the terminal. So first it will create the use the block mesh, then it is going to use the set fields to create the initial field values for the means alpha given in the 0 folder. Okay, then it is going to use the application. This application is defined in the control dict. Okay, so from where this it is getting the information of this application. So if you see the system control dict, so you can see that application is the enter form. Okay, so from there it is taking the information of the this solver and it is going to run the all run. Okay, so similar things it is doing this all run, but we are doing one by one. It is doing this all command at once. So this is difference between the all run, and since I am means I am taking the tutorial classes, so I need to specify the each and every command that I am using. But if you want, you can run this all run command at once only. Okay, so if I run the block mesh, so it is going to create a block mesh. Okay, now if I go to the 0 folder, so you can see here that there are three variables are given: u, this alpha dot water, and this prgh. Okay, this alpha dot water dot or arg value that is given here, this is just given to keep a initial level information. Okay, means what I mean to say that if you open this alpha.org, it is going to give you simple boundary condition. Okay, this information is given here that initially the value internal field value is 0, the dimension is 0, 0, 0, and these are the different boundary field. But as soon as you are going to run the set field dicts, it is going to change the every value of the alpha dot water. Okay, so that is why one file is already stored in the test case, that if someone wants to again run this set field command, it is going to just copy and rename it. Okay, so if I copy and rename it, if okay, so OpenFOAM interform solver only going to understand these three variables. This is just kept it as for the means you can say the for the your help, that this if you want to do the set fields again and again, then you can just copy and paste it and you can just rename it as the alpha.water. This is why this folder is always kept as a .org kind of thing. Okay, OpenFOAM means only read these three variables. OpenFOAM don't read the this .org variable. Okay, so if I means if I open the set field dicts folder, so this is the available in the system, this set field dict. Okay, so this is the set field dicts and that is defined for the alpha.water. Okay, so it is saying that by default every cell has 0 value. This line says that by default every cell that is given in the mesh should be have 0 value. Okay, now it is going to create a box of given this dimension. Okay, so the minimum dimension of the given box is the 0, 0, -1, and maximum the given dimension of the box is the 0.1461, means this point value. So all the cells located between this minimum value and this maximum value is going to assign of this alpha.water equal to 1. So this is the meaning of this complete complete command that going to select all the cells between this minimum dimension and this is the maximum dimension, and all the cells centered of the given cells between these two minimum and maximum points is going to assign a value equal to 1. Okay, so here the value is 0 and here the value is 1. So only those cells who has the dimension minimum dimension this and maximum dimension this is going to assign this value. Okay, so once you are going to run the set fields, so first let me run the block mesh, although I have already run. Sorry. Okay. Now if I type here check mesh, so we can see here that we have a number of cells equal to 2268. Okay. So this is the information of all the cells. So all the cells are created as the hexahedra cells because block mesh by default create the hexahedra cells. Okay. So the total number of cells are the 2268 number of the cells. And when we type the set fields, okay, so you can see here that so all the cells given between the 0, 1 and 0.1461 to 0.29221 is assigned value equal to 1. Okay, let me create one .foam folder. Okay, and let me open it in the Paraview. So in the folder. Now suppose you want to solve this problem, that you want to use that dam break case only, and you want to create a sphere, means you want to assign a value that alpha dot water equal to 0 of sorry, let it be 1, that alpha dot water equal to 1, and you want to create a sphere that of radius 0.05 and the location is 0.4, 0.4 and 0. Okay, so this problem we want to solve, and we want to use the sphere to cell using the set field dicts. Okay, and you want these two variable you have to assign here, that you want to assign that alpha water equal to 1 and u equal to -1, 0 and 0. Okay, so just use the dam break case and try to solve this task. Why it is showing the error? Some mistake. Paraview is showing some error. Everyone is getting error, or you are able to open the folder. Just write in the comment.
Hello everyone. Till Pratyush is coming back, I have attached an PDF in the WhatsApp group that is on the dam break case. You guys can go through it, like have a look at it. It has a lot of information for the present case. Till Pratyush is coming back, you can have a look at this PDF which I have sent in the WhatsApp group. I think I am
Gurban,
able.
what levels as you are saying? Can you type in the chat? Yes, yes, I thought that. Okay, so if similar to me, if someone is facing the same issue, then you can change this level size. Earlier, in my case, it was 32-bit, but if you are using the 64-bit, then you should have to change here. Okay. So now we are going to solve this problem. Okay. This we are going to use the same dam break case, and we are going to create a sphere to cell, and we are going to specify alpha water equal to 1 of radius 0.05, and the origin should be 0.4, 0.4 and 0. try to do by yourself. I am also doing. Why paraphone is not showing this? Paraform is not reading this zero value correctly. Okay, maybe you can use in Ubuntu. So let me run this interform solver. So basically means what I want to try to obtain here. So I want to give this alpha value is equal to 1 for given this box in the specified in the system set field. Maybe you can understand from the different time step. Yes. So this is another means .foam I've created because means zero folder it is not able to read this form in OpenFOAM. I don't know why this issue is happening, but this is not able to read the zero folder. But apart from the zero folder, you can see here that this area, this given box area, this complete area is given as a one field, that is the water value equal to 1, and rest area is considering it as a air. Okay, so this is kind of a multi-phase problem. Since it is not showing a zero folder, that is why you are seeing little diffusion here. Okay, but in actually in zero folder, this is the black box, complete box. This is that is the value equal to 1, and rest has the value equal to 0. Okay, now if I go to the next, then you can see that slowly this diffusion is increasing. Okay, and there is a one dam is specified here. Okay, so this is, you can see here that this value is uh, solving this interface, how this interface capturing is happening, and how it is interacting with the dam, that you can see here. Okay, this is how it is working, and the maximum time step is the 20, and so this is the solution after 20th iteration. Okay, now the problem that I have given is that, so if you see the means x dimension of this complete box, so this is one kind of the 0 point up to dimension is around 0.5 into the 0.55. Okay, now I want to create a radius of 0.05 at a location 0.4 to 0.4. Okay, so this is the 0.4 and this is the 0.4. So here I want to create one sphere, and here I also want to specify of the alpha dot water equal to 1, and rest will be rest value will be 0 only. Okay, so this problem we want to solve. So what should we approach here? What should be your approach here if you want to specify the set field? Okay, so you create the set field using a text editor. So using text editor, you open this text file, and so let me copy this only, and let me paste here. Okay, now if you I want to check that what are the different options available here. So yeah, I type test as a random name, any name randomly you can type here, and if I clean the folder, I'm not cleaning the mess, I'm just cleaning the folder only. Okay, and if I type the interform, sorry, if I type the set field dips, so you can see here that different information is given here. It is saying that the topo set source test is the wrong unknown type. We have a this different option of this set field zone. Okay. Now since we want to know information about the sphere to cell, because we want to create the all the cells, we want to select all the cells lies between this given is a cell. So we can means find this sphere to cell information from a given OpenFOAM tutorial. Okay, so let me open another terminal and let me create the OpenFOAM 6 environment, and we can just go to the home tutorial folder. Okay, and using this grep command, grep -r and this sphere to cell, we can find out the what are the different test cases available in the OpenFOAM. If you go to here, there you can see that here it is given one test case. Okay, where you can find this sphere to cell information. Okay, now if I open this set predict using the vi editor. Okay, so you can see here that the information about this sphere to cell can be written in such scenario. So you have to specify the center, you have to specify the radius that you want to create, and if you what are the different field values that you want to modify, that information you have to write here. Okay, so means that I have to first write that I need to have sphere to cell information. So instead of the test, I have to write the sphere to cell. Okay, now the different information that you need to write, that first specify the center. So using this syntax that I am showing on the screen, using this syntax we can follow the same instructions as you are seeing on the screen, and you can do the modification here. So in the center we have to write 0.4, 0.4 and 0. Okay, similar to here, and again we need to write the radius. So if I write radius, and the radius I want to specify is of 0.05. So 0.05. Okay, now this alpha dot water that we want to keep as 1. So this value we want to keep as 1, and this again we want to specify the u, that is the velocity. Okay, I can copy, and we can write here this, since velocity is the vector field, so we can write the velocity vector, and here we can write the u because we want to modify the u, and the syntax of the u is that we need to have the 3 component, that is the -1 0 0. We need to write -1 0 0. Okay, so this is the way you want to create the spheres to cells, and here you can want to specify the different field value that is specified in the 0 folder. Okay, now again we can clean the folder. Okay, now we can create the block mesh. Okay, and we can use the this set field. Sorry, I So I'm this center the keyword center I have taken written as wrong. So spelling should be C and T R E. So that is why it is showing the error. Now if I run the set fields, you can see here that it has means changes the value within the given box and also changes the value within the given the sphere. Okay, and now you can run the solver, and since this 0 folder is not running here, so I am not able to. So let me try once again. No, so it is not. No, unfortunately, it is not reading the 0 value. Okay, but you can see on the screen that it is modifying the value within the box as well as it is modifying the value within the sphere. Okay, so this way you can use the different pre-processing tools for specifying the changing the variables of the 0 field. Okay, and I am going to give you some other exercises that you can use to uh, run the test cases, and you can go through the different FB schemes. You can go through the different FB solution, and maybe you can go through the different control dict commands. And I am also going to share the different master text file for control dict, FB scheme, and FB solution. Okay, now at the last, I want to give you some touch about the programming of the OpenFOAM. Okay, so in the next workshop, that is the scheduled in the next week, you are going to just understand the C++ programming based on the OpenFOAM environment. So let me give you some touch about the OpenFOAM programming. Okay, so means here I am going to means I am not going to tell you that how you can add a temperature equation in OpenFOAM. Just I am going to show you that means what are the different folders, what is the default structure of a means solver available in the OpenFOAM. Similarly, like we have done for the test case, let's understand that what is the different structure for the OpenFOAM solver. So when you open a solver, then you will going to find out there is one make folder that is important, and there is one .c folder. Okay, and there is one .th folder that is the header file. Okay, so what I mean to say that suppose you want to create a solver with the name of the hello world. Okay, so you can use this home new app command to create a new solver, and the name of the solver will be this hello world. So if you create here, then you can see that it is saying that creating the application code directory with the name of the hello world, and it is also making one subdirectory with the name of the make. Okay, so if I go to the hello world, so you can see here that there is a one .c folder and there is one make folder. Okay, so this is the basic requirements if you want to do any solving, or if you want to make any utility, then this is the basic requirements, that there should be one .c folder and there should be one make folder. Okay, now let's understand that what is there in the make folder. Okay, so in make folder there is two files, that is the text file that you are going to see, one with the name of the files and one with the name of the options. Okay, what is the files? So in files, it is showing that we want to compile the solver, that is the .c. Okay. So you want to compile the source file, that is the .c. Okay. So this is the solver that we have created, and here there is one .c folder. So OpenFOAM only reads this .c folder. Other folders are just snippet codes given in the this source file. Okay. So open, as long as you are going to write wmake on the screen, it is going to read this .c folder, and once you have complete the compilation, it is going to create a one app with the name of the hello world, and it is going to store into the this form user app bin. Okay, so it is going to store in the form user app bin with the name of the hello world. Okay, so it means that whenever you type a ICO form, or whenever you type a simple form, actually this app has been created by after compiling a solver with the name of the ICO form. Okay, so this is the way of the compiling a open form or any kind of solver. Okay, now let's open this .c folder. Okay, so if we have done any time, if we have done any C++ programming, basic level of C++ programming, from next tutorial I'm going to use the Ubuntu terminal, because this WSL is not it is taking too much time to open even a text file. So next time I'm going to use the Ubuntu. So if you open any C++ programming, even if you're using any other software or any other tool, then you are going to find this header file. Okay, so generally if you are going to code a OpenFOAM programming, then generally we include a iostream.h. But OpenFOAM, in OpenFOAM we always use the fbcfd.h. So this is the, you can see that everything related to the OpenFOAM namespace, or this int main, the coding of this int main or int rc, or the character RGB. These all things are included in fbcfd.h. Okay, so this
Hello. Can am I audible to everyone? Can someone like say if I'm audible? Hello.
Yes, Abhishek, you're too good to listen.
Okay, okay. Thank you, Rajiv. Actually, there is problem with Pratyush PC. It has suddenly hanged. I very like we regret to say or to say this to all of you that we have to end our session right now at this point because his PC is not working. His laptop has just hanged. So we'll start if nobody has problem. We'll start from because it's already 9:50. We'll start from the same point with in our next workshop in the next session. And meanwhile, you guys practice all these cases of dam break and cavity cases, whatever. We'll keep sending you the material for that. And in between, if you guys have any problem, you can text us, WhatsApp us, or contact through any means if you guys facing any problem.
Definitely, Abhishek. Thank you. Thanks for the information.
Yeah. So sorry for this. Actually, his PC laptop has suddenly hacked. So again, I'm telling this. We have to stop this, and we'll continue from the same point in the next session. Thank you for
Abhishek,
a.
can you make sure that like we'll be having this access for this today's video
Yeah. This video will be uploaded by tomorrow. Like
by
his
tomorrow?
PC, like his
Definitely.
PC is hanged, so maybe
Yeah,
today he'll. So by tomorrow it will be on YouTube channel. You can see, and you'll have the access through other means also.
definitely. That would
Yeah.
be fine. Yeah.
And
Thank you,
if
Abhishek.
you, yeah. And if you guys have any problem, you guys keep practicing these tutorials, because practicing is the main part. If you don't practice it, you'll forget. And the next session, you'll be like a more of a newbie, like what is happening. So I hope you guys practice it all throughout the week. And if you face any problem, you can text us. We can like help you out. WhatsApp us, text us, or anything. Thank you, everyone. Thank you for joining.
Thank you. Thank you very much,
Okay,
Abhishek.
Rajiv, see ya, man.
Thank you,
I'm
man.
looking forward to meet you.
Thank you.
Maybe next week. Yeah.
Yeah. Before the class, maybe we can have a little
Yeah.
conversation.
Sure.
Thank you very much. Yes.
Okay, everyone. Thank you for
Mhm.
joining.
Jamshid, are you there?
Yes.
Jamshid, where are you from?
I'm originally from Iran,
Uh-huh.
but
The previous class I heard you're from Finland, right?
yes, now I'm in Finland.
You're in Finland. I'm right now in Riga, Latvia.
Uh-huh.
So quite neighbors,
I see.
neighboring countries.
Yes,
Okay. Neighboring countries. I was a
thank
bit
you.
surprised. Thank you, Jamshid. So quite
Thank you.
we look forward, yeah. So which part do you live in Finland?
Follow.
Oh, yeah. Yes.
And how about
I,
you?
I am right now doing I finished my first year PhD from Riga Technical University,
Uh,
Riga, Latvia,
uh-huh.
RTU.
Uh,
You know by any chance?
no,
Okay. Okay.
thank you very much.
Okay, okay, Jamshid. We'll see you next week, yeah? Ciao,
Yes,
ciao,
of
ciao,
course.
ciao, 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 ciao.